Hi, good evening. It has been a long time since I made a video, and today I'll try. I was thinking of making a video about XPS. I was a bit busy during past couple of months with my work and then moving and here and there. Now I'm in a different home than I was previously. So let's get started. With XPS, let's say generally you get data in some form of. You have a good software called CasaXPS. So this is You can also try this in Origin, the deconvolution of XPS peaks, but I always suggest Casa because it is easier and much more intuitive. So when you get an XPS data, preferably you get a Casa XPS file or some file which can be easily opened in Casa, or at the max case or at the worst case you get an Excel file, which is here what I'm showing. And how should I convert it into a Casa file? We'll also see that. So let's say I have an Excel file with all the elements. What I do, I just open it, do enable editing, and then in the file, just save this as in the same folder, whatever you have. This text tab delimited. You see this option, text tab delimited .txt file, and then whatever element that you have selected here. This is the ni2p scan. So always save that in the same name, that is ni2p. You select here text tab delimited. You just put ni2p. That's it, and just save. Whatever comes, just press OK. Then you have CO2p, same, save, text tab delimited, CO2p. Then you have, let's say, manganese, Mn2p. Then you have, I think this is fine, 3 elements. You always get a spectrum of carbon even if you have not requested it, or if sometimes they don't provide. Don't forget to include the carbon element when giving your sample for analysis, because C1S is the most important one you have to have. Even though your material may not have a carbon, but still you need to have a C1S spectrum. I'll tell you why it comes. And so we have survey spectrum here. Just save as survey. Fine. Okay, so after you get that, in the same folder that I have, let's say, Mn2p, Ni2p, survey, C1S, CO2p. Now go to the CasaXPS, then file, convert and match, and select, go to your folder wherever it is there. So I have select all of these files. If you have many files, just put them in a separate folder in here. So it just Control A and then do open. It just says transfer existing variables. Yes. So you get these labels here: C1S, CO2p, Mn2p, Ni2p, and then survey spectrum. The thing with C1S is, like, suppose my material does not have carbon, but then I get the C1S spectrum because when we give a sample for analysis of XPS, the sample is first stuck to a carbon tape, and then it is put on the this, like, I'll show you an example like how it happens. For some reason, I don't know why my pen is not working. Okay, fine. So the thing is that the carbon, I'll try to repeat it. So our samples are, there's a square grid kind of, it's a mesh grid with very fine mesh, and then there is a handle or something which is which goes, this whole thing, this goes into the XPS machine or XPS instrument. So on top of this, what for analysis we do is we put, or the operator whoever is there, they put a carbon tape on this, and then there is your sample on top of the carbon tape. So even though your sample does not have carbon element is present or the carbon content, it still gives the signal of the carbon type, and this is very useful in XPS, and we'll just see why. Because the XPS that we get, these spectrums or the spectra that we get, it is not calibrated, and carbon is most useful for calibration of this XPS. What I mean is for calibration is these values are very um, sensitive to the binding energy is very sensitive to your elemental state. Suppose I'd say CO2p. Now it is at around 780. After I do calibration, it goes a bit to the left or to the right, but then the 780 is what now it is there. The 780, it is not correct, so we have to do calibration. Maybe you see this 780 as let's say this is CO, so you think maybe it's a CO2p 3 by 2 peak of CO3 plus, but once you calibrate it, you get to know it is not. So don't make wrong conclusions with it. Always calibrate your samples first, and for calibration we need the C1s peak. Okay, so now we have the XPS now opened in the Casa. Just save it, save as Casa, whatever name you want to give, same folder. I put test or something, whatever my sample name, example 1, save. Now it is saved. Now you have to go to options and then processing. You can also go to the processing using this icon here. So once you get processing, just go to calibration, and in the calibration select the highest peak of C1s. Maybe this has a very singular peak, that is just only one peak. If you have a peak here also and a peak here also, something here or something here, you have to always consider the highest peak, that is which has the most intensity. Try to get as close to the exact value as possible. Just click it here. It will take measured 284.776. The value of C1s is 284.8. It is the value always. Uh, Let me once check, I'm not sure of it. So, yes. So, the value is 284.8, what I saw was correct. And so we just put it here in the click. It says 284.776. It's the measured value, so you put true value 284.8 and just don't do apply. You select all the components. Just keep your hand on control. There is press control and click each of these. So you have selected all of the components. Then you say component here, or sorry, to the apply to selection. Sorry, I have not used this software since quite few months, so I've forgotten, but still I remember some things. So you just put apply to selection, not apply, apply to selection. You have to select all of them, then apply to selection. Once you're done, in the processing history you can see here calibration measured equal to 284.776, actual equal to 284.8, binding energy add whatever it has done, it will show. So if you want to remove calibration also, you can do that. Just select it and then remove or reset, whatever. If maybe you think that you have done a wrong thing, just reset. It is fine. Now that you have calibrated your spectrum, let us see. See, the shift here is minor, but in some cases you can see that the shift is a major one. Sometimes it happens when the instrument is not correctly calibrated or something. So always having C1s is very helpful, and you have to always calibrate your spectrum before analysis. Now that we have calibrated and I don't have carbon in my sample, I'll just leave the C1s. I'll go to CO2p. Next, to analyze the CO2p, what general method I prefer is, for a similar material, I'll see the research papers or literature, how many peaks or what kind of peaks can I expect in my material, or else you also have this wonderful database of thermo um, XPS database. It's a very good resource. You have each element, let's say CO, it just goes to CO. It says that you have CO2p 3 by 2, and this is the spectrum that we can have. So once I'll just plot side by side, you can see the pattern that we got is correct pattern of cobalt oxide, and This was an cobalt oxide or a high entropy oxide. So, but still you can see that the pattern is kind of correct. 780 similar values. So you get to know that okay, my material, this particular CO has four peaks, which is CO2p 3 by 2 and CO2p 3 by 2 satellite, CO2p 1 by 2 satellite, 3 by 2, 3 by 2 satellite, and 3 by 2. So you have here all the values that like or the you have majorly four peaks in this. If you don't know or you are doubtful, it is always better to first check literature, and if it is not available in literature, then come to the thermo XPS database, because maybe this is for or this database is for generalized database, but your material may have different states, so better to check literature first. But now we know that there are four peaks, so this is all 2 plus, COO, that is CO2 plus. So I just do a fitting. To do that, there's a icon here, quantify. It has a teal color highlighted symbol here. Or you can also go to this options and then quantify, yeah, quantification parameters here. So first there are two things in each analysis. One is the region, and second are the components. So once you have to, or the components always come in a region, and the region is defined for an element. Like there for a CO2p, there will be one region, and inside that region there may be four components here. So I just create one region. I take it as close as possible and or as better. See, and also if you have a peak like this, make sure that this touches the background line that is there. It touches this point, because what happens is if you take it here, see, it is not touching, so your analysis may be wrong. So you have to select the region bounds or this region limits such that the background is visually correct, or what you can see is there. You see this is the background that is there, but still, but you have to see that the background is always correct. Then there is background types. I have selected Shirley, or by default it selects Shirley. If you click on this BG type, you get a list of values. People also generally use Taugard, so you can use Taugard. Maybe this does not change here much, but I'll tell you the difference that I have observed. Sorry, once you select Taugard, just press OK. You have to press enter. If you don't press enter, you just click elsewhere, it just goes back to Shirley or the previous whatever background is there. So select the background, just press enter, so it has selected Taugard. See, so I'll tell you a simple thing. What happens is, suppose you have a spectrum. So for a Shirley background, it always goes this shape. This is Shirley. And for a Taugard always goes sorry. Taugard always goes like this. A kind of very elongated, very elongated U shape. This is Taugard. Then you have also linear background, which it's just in weighted endpoints. So not just a straight line. Sorry, my line is not straight, but this is the linear background. So now you understand the difference between Shirley and Taugard. These two are mostly the used backgrounds, the Shirley and then Taugard. So generally people report Shirley background or Taugard depending on how their pattern is. So our pattern is somewhat like this. Okay, I'll show you an example. Our pattern is this endpoint and this endpoint are not on a straight line. Like if you plot it and these are not a straight line. So you need a background which covers both of them. Like Shirley would be a perfect example for this, but if you, so as I said, our peak should touch this, so this should also happen. But then if you take Taugard background, you can see it just does not touch. So that's what we see here. So depending on your endpoints, you can select which background type you want. And also whenever you select the background type, you have to keep it constant in all the elements. That is, if I select Shirley here for CO2p, then for Mn2p, Ni2p, it has to be Shirley background. And while writing, you have to mention that the analysis is done using a Shirley background with XP, like the XPS analysis is done using taking a Shirley background or something like or Taugard background. Now you see when I take a tau guard background, this does not touch because these endpoints are not on the same intensity or the same Y scale. So I take a Shirley background. It has no touch. You can see the elongated kind of inverted or bent, not bent, some S at 90 degrees. So this shape is there. Once you have that, now comes the components. There are four components as we know from here or from your literature. How many? So we just create four. The fourth one did not come here. Just pull it, and now you have four components. Now the thing is you have to fit components, keep fitting, keep clicking until these numbers stop changing. And also you have a here option just beside the PG residual. So you have your chi-square value just to keep fitting. It keeps reducing and do this until you get a perfect fit or the numbers don't change. So here the numbers don't change now. So this is correct. Like the fit has fitted. Sometimes what happens is some of these numbers get turned into red color. So I'll show you an example. Like now you do keep fitting. Yes, maybe there was a component here also because the chi-square has reduced. So better to consult literature than the database. I think these numbers are keep on changing, so I think I'll stop here. You get the point. So we have here sometimes I want to show the red numbers. I don't know, and it's still fitting, so I don't want to go in this one. Still, let's leave it at this. But you get the idea how to fit a thing. Once you get the red numbers, it means that that peak is wrong, or you get negative FWHM or red color. Any number in red color means that peak is wrong. So just click it and cut it. So because it is wrong. So now it has happened. This is done. So you can name them if you want. If you don't, there's no need. CO2P1 by 2 or whatever it is. I'm just randomly naming. Always press enter. Clicking elsewhere does not work. It's just for your labeling in here. But anyways, that you are going to plot in origin, it doesn't make much of a difference. So up to you. Then CO2P is now done. We go to MN2P. Repeat the same process again. This create a region, select the endpoints correctly. See, now that I've selected this background goes above the line, this does not, this is wrong. So I have to take these endpoints correctly, and even though I'm getting into the peak, then only this is selecting, which means this also has a gap. That is like there is a peak here, else it when I brought it closer, it should have touched. That is not touching, which means that this there is a peak here or something here which is stopping it to touch. So I should not forcibly make it by putting something like this because now I have lost my peak area in here, this part of area. So your intuition should work here and don't do mistake here. There is a peak here, so consider that. Then after you take components, component. Now that your component is like this, you can pull it or and vary the shape. Once you take inside, it goes thinner and some things like that. Once you start using, you will get to know how these peaks shift or change their values, or the shape of the peak, how you can change them with your mouse. Always when doing it, first consult your literature, then make a rough estimate of, let's say, I think like I saw some paper where this says that it has four peaks. So first roughly put all the peaks in their intended positions and shapes. So once you have this, just put it like this. Now do the fitting. Don't put four peaks continuously in a row and do fitting because it will take longer time. It won't converge correctly. Better to put them in a good shape or however you like it, then start fitting. So it makes it easier for fitting. So keep on doing that fit components and it happens. Now another thing is whenever you fit some, let's say this peak is there, not very Okay, I'll explain with this purple peak itself. Whenever you do a fit, your peak should not come like this. That is, this is already a peak. Let's say I'll remove the other. So you have here one peak, that is the light green color peak. Then you have the red color. So this kind of situation should not happen because this is wrong. Always your second peak should have at least some area different than the first peak. That is, they should not completely overlap because this does not make any difference. Like you suppose you have a peak like this, one component or one peak, and your if second peak comes like this, that is correct. But if there's a peak like this and then your second peak also comes like this does not make any meaning, because here let's say you add something, let's say some x value, and then this peak has some y value, so you have some things to add. But here there is no meaning because it just increases the intensity, and you can always do that with just the one peak. So don't do this mistake. Your peaks should not completely overlap. Some papers do it, it is wrong. You don't do that wrong. Once you, okay, I'm leaving the mn2p here. Same thing with ni2p, you consult the database or your literature, then fit the peaks. Now that you have done everything, we go to survey spectra, or in the survey spectrum it's very easy to do. Just go to library. I know CO, mn and ni are there. Go to periodic table, just put CO. It has come CO2p 3 by 2, this one, mn, mn2p 3 by 2, this peak, and nickel has come this. So just first touch, like click one and label your plot in casa, then click another, label that plot. That's it. I'll now show the labeling. Now that we have CO2p, I'll show how to do go plot this. Go to here, tab, just tab, sorry, not tab, the emb, just the button beside it, emb, or whatever it is written, I can't read. I think that's an emb. So once you get this, you get this big table kind of dialog box. Copy all to clipboard, go to origin, just paste it. Once you have done that, you rename whatever you want, like CO2p. After you do this, you have here all the long names: kinetic energy, binding energy, CPS, CO2p, all the components here. Then you have envelope, then you have background. So these are the components, and this is the envelope, background, all these things. With these plots that come out, come out x-axis as kinetic energy. You should plot always as binding energy. So because kinetic energy is used in auger electron, not XPS, so just select this and press the delete button. Don't right click and delete because the whole column will go. You just need to press delete button. Then cut these two PC columns and paste them at here. Then the last column and here. So what you have is first column, delete button, second and third column, cut and paste in first and second column, then the last in the third column. This is the thing that you should follow. The logic I'll tell you. Um, so now you have here X as binding energy, which is your x-axis label, Y as CPS, that is counts per second, which is your raw data, or the thing that is visible as a red color here, the raw data. Then this is the envelope. Envelope means this one, the line after, like the superimposed line on the red color, that is the addition of these two peaks here or some full spectrum. So this is your envelope. Then you have here your components. So I have named it, so it has come as a name. Then or else it just comes survey. then at last is your background. So this is the logic. You just cut the last one, paste in the third, first two in the first, the second and third in the first. Follow this logic, you will be fine. Select all of them, just plot. So now you got your spectrum. While defining the limits, you want to make a nice plot, go here. You have here 810 and 776. So always the XPS plots are plotted in the opposite direction. So now it is 770 to 820. It should always be 820 to 770. That's a historical reason. The reason that when XPS was first done, these instruments measured in the opposite way. So research has been like the papers that we publish do it in the opposite way, even though we have computers and all. So that's a convention we use. So just follow that. 810 to 776. Just round off to the nearest number and plot it. That's done. Your XPS has now come out in a nice pattern. You just make your plot whatever you want. Write CO2P here, and then just remove this intensity. Write CPS intensity, all this binding energy. Label the plot whatever. This is done. Now I'll show you how to do the survey plotting. Go to the survey spectrum. Same EMB. Copy all to clipboard. Here also same thing. Kinetic energy comes. You don't need kinetic energy. Just delete it. You just need the first two. You don't have a background in survey, so take these two, plot it. Your plot has come. Same, reverse the scale. Now that it has come, just put side by side. OK, take it and then write here is the CO2P, CO3 2P3 by 2 here. So I think this is the CO2P3 by 2, 900 something. I'm just roughly marking it here, but you verify and mark CO2P. And then similarly, let's say this may be an Ni2P. So you just put Ni2P and label your plot, and that's it. So this is how you do the XPS analysis. Thank you. Have a nice day.